So hi everybody, I'm Celine Armand, and in this video I'm going to present the work on the gamma ray image reconstruction of Andromeda galaxy that we've done with Francesca Calori. I'm going to start this talk with a quick presentation of the source. So M31, or Andromeda galaxy, is a spiral galaxy located in the southern hemisphere at a distance of 785 kiloparsecs. And in optical light, this galaxy spans 3.2 degrees by 1 degree, and it is said to be similar to the Milky Way galaxy. And let me do now a quick review of the previous studies about the extension of the source in gamma rays. So in 2010, Fermilab detected it at 5.3 sigma, but only found a marginal evidence for its extension at 1.8 sigma. Then 7 years later, Fermilab performed a second study with additional data and detected the source at 10 sigma this time, with a weak evidence at 4 sigma for the extension. And after 2017, various studies have been performed using multiple templates, but the authors still report a weak evidence at 4 sigma TAUPs for the extension. So the goal of this study is to characterize the morphology of M31 using an adaptive template fitting technique with the code SkyFact and the Fermilab data. So this code consists of a hybrid approach between template fitting and image reconstruction, and was developed by Christophe Weniger, Emma Storm, and Francesca Calori to study and decompose the gamma ray emission of the sky. The code is based on a Poisson likelihood minimization, including nuisance parameters, and makes use of a spatial and a spectral models for each of the components, weighted by a normalization factor. And the freedom of the parameters is controlled by what we call hyperparameters in the code. So for the data part, we use the Fermi science tools to prepare the count and the exposure maps, and to produce the PSF maps that we need in the code. So we prepared 624 weeks of P8R3 data with the pixel resolutions of 0.05 degree over a region of 10 by 10 degrees and an energy range of 0.3 to 100 GeV. And for the theoretical part, we have to model each emission component. So for the background and foreground components, we have the isotropic gamma ray background. We also have the galactic diffuse emission, which includes the inverse Compton, the pi0 decay, and the branch radium. And we also include 13 point sources based on the fourth catalog of Fermi. And we also need a model for M31. So we use the spectral shape given by the fourth catalog of Fermi. And we also prepare various morphological models, such as the 2D Gaussian, the uniform template here, which both are motivated by previous publications. And we also create INASTO models that correspond to more realistic distribution in the nucleus, the bulge, and the disk of the galaxy. Now that we have all the key components, we can perform the analysis. And in this study, we use 3 different modes, which are the standard template fitting, where we have the least 3 parameters, then the semi-adaptive template fitting, where we increase the number of parameters. And finally, we have the full adaptive template fitting with the highest number of 3 parameters. So let me start with the standard mode, where the spatial part is kept fixed to the model and the spectral part is left free to vary. So on the left side, you can see the residual map of the fit without the M31 component. And the map clearly shows an excess at the M31 position. But if we include M31 into the model, using here a Gaussian of width of 0.001 degree, so that it's close to a point-like source, the excess residual here is absorbed. And the results of these fits show a detection at 7.8 sigma of M31 as a point-like source. We now want to characterize the extension of M31 with a scan that we perform over the width of the 2D Gaussian, ranging from 0.001 to 1 degree. And we use a cubic spline to fit the likelihood values versus the extension angle. We find a best fit value for the angle to be 0.48 degree with an evidence at 9.2 sigma for the extension. So this value for the extension that we found is compatible with the value of Dimoro et al., who found a value of 0.42 degree using a 2D Gaussian template as well. We now move on to the second analysis mode, the semi-adaptive template fitting, where the spatial part of the background and the foreground components is now free to vary while the rest remains the same. So we performed 3 different scans over the extension with different freedom on the diffuse components. And we obtained compatible results with the standard mode with an evidence for the extension of 6 to 8.8 sigma. And by comparing the results flux for M31 with the different configurations here, we see that the reconstruction of M31 flux is robust against the freedom allowed on the parameters. And we also do the same exercise using a uniform template for M31 from an angle of 0.025 degree, which corresponds to only 1 pixel on the map up to 1 degree. And in this case, we found 2 minima, one at 0.4 degree and the second at 0.95 degree, with an evidence at 8.5 sigma for both. And both extension angles are compatible with the previous publications. The first one with the value of Dimoro et al. Of 0.33 degree using a uniform template. And the second one is consistent with the halo of radius 0.9 degree of Firkov et al. And the last spatial templates that we use in this semi-adaptive mode are the 3 anisotrope profiles to model the nucleus, the bulge, and the disk of M31. And we performed the fits of all possible combinations with either single or multiple components to model the galaxy. And we found the highest evidence at 9 sigma for the nucleus and the disk model, and also for the bulge and the disk model. We note that the addition of the nucleus or the bulge to the disk only gives a marginal evidence of 0.8 sigma only. So here we clearly have a preference for a disk-like structure, which is in agreement with our previous results, as we have an extension of the anisotrope disk of 1.08 degrees semi-major axis compared to the angular radius of the uniform disk scan that we obtained with a second minimum of 0.95 degree. And so far, we only compare models that were submodels of others and that are called nested models. But what if the 2 models are non-nested? How do we compare the resulting likelihoods of the 2 if they don't have the same number of free parameters in the first place? And this is what we're going to see now. So far in the literature, there's no such proper comparison. And in this work, we focus on the comparative aspect using the ICAI key information criterion. And this method allows us to compare non-nested models by taking into account the number of free parameters that we have in each fit. And based on this AIC score, we can make a ranking of our models. So we make the comparison of all our models 2 by 2 and find that the uniform models best describe the morphology of M31. So let me now present the results of the adaptive template fitting mode, where the spatial part and the spectral part are both left free to vary and adjust to the data. So here we do not assume any morphology for M31, and we reconstruct the map from the photon absorbed by the M31 components in the fit. And from this reconstruction here, we can then extract the intensity profile using concentric annuli spaced of 0.1 degree from 0 degree to 1.5 degree. And these annuli are centered around the source position given by the 4th catalog of Fermi. And we try to fit this intensity profile using various functions. And the best fit is given by the sum of a Gaussian and a power law that you can see here. The Gaussian would correspond to the source itself, M31, with a very large sigma here. That implies that we have a rather flat profile, as you can see here by this curve in purple. The power law here suggests that we have a second component that could be either the outer part of the disk or the cosmic ray halo, or it could indicate the presence of M31 bubbles. Just like we have the Fermi bubbles in our Milky Way galaxy, which are these giant structures lying above and below the galactic center. And let's go back to the intensity profile and have a closer look to the curve, where we find an inflection point at 0.3 degree that could delimit the apparent size of the bulge in gamma rays. And this value that we derive here is compatible with the 0.33 degree of Dimoro et al. Using a uniform template. And it's also marginally consistent with our first minimum of the uniform disk scan at 0.4 degree. At the end of this study, we compared the reconstructed flux of M31 with that of the Milky Way. And we see that the M31 emission is not compatible with our galaxy interstellar emission, but rather with the spectral flux of the galactic center excess, as we can see on this plot here. So whatever analysis mode we use, the spectral flux of M31 follows the profile of the galactic center excess in dark purple here. We also note that the two leading hypotheses for this galactic center excess is either a dark matter component or a non-resolved source population of millisecond pulsars. We also did the analysis of the galactic center using the same adaptive template fitting technique, where we show that the data prefers the MSP scenario over the dark matter hypothesis. So let me conclude on this talk. So we study M31, the closest spiral galaxy to the Milky Way, to characterize its morphology using the code SkyFact and 624 weeks of Fermilab data. And we use 3 analysis modes to carry out this work. The first one being the standard template fitting, where we use a 2D Gaussian to model M31. And we found an evidence for an extension at 9.2 sigma. The second kind of fits was the semi-adaptive, where we tried several kinds of spatial templates. And we saw that we had a preference for the rather flat models. And the last kind was the full adaptive template fitting, where we reconstructed the morphology and the intensity profile of M31 without any prior assumption, which gave a rather flat profile as well. And finally, we compared the M31 emission to that of the Milky Way galaxy, and we saw that the M31 flux is compatible with the spectral flux of the galactic center excess that could be explained by a non-resolved MSP population. And this work could be carried out further, where we could explore the MSP scenario with an analysis using a template model for millisecond pulsars. Or also, we could explore the dark matter possibility with the addition of a dark matter component to the fit. And the latest telescope arrays, such as LASSO or CTA, could help resolve the M31 component that could include a possible detection of an interstellar emission component. And I want to finish this presentation by mentioning that all of this work was published in PRD a couple of months ago. So let me know if you have any questions, and I'd be happy to answer them. And thank you very much for your attention.